off on Hodge Theory, and so today the goal is to finish the discussion on Hodge Theory. So we need some observations. So I'll use lowercase h to mean the dimension of HK symmetrical. And so the observations were that if M is compact and closed, then what happens is HK equals Hn minus K, and this is known as Poincare Duality. And H, if M and N are compact and closed, then we have HK of M times N, which is part manifold, is equal to the sum of I plus J equals K of HI of M times HJ of M. And we could categorify these statements, which means replace numbers with vector spaces. And so this guy becomes HK is isomorphic to Hn minus K. It's called Kunneth Formula. And then this one becomes HK M times N is equal to the first sum of HIM insert HJM. And to prove this, we wanted special.
Can I ask you a question, Taresh?
Yeah, 1 second. Special representatives, yeah.
Do you think of Poincare duality in a similar way that you think of Stokes' theorem? In the sense that, like, once you have the right language to think about it, it's kind of obvious? Or do you think about it as, like, somehow more non-obvious?
There's an idea of it, and it's not, like, the theorem itself isn't really obvious at all. Like, in this case, it's not too hard to show, but in the integral case, like, it's a lot more technical. But the way I think about it is, like, the main idea is the intersection pairing that we discussed.
But it's non-degeneracy. Like, do you think of that?
Right, and you just, like, hope the non-degeneracy. I mean, like, that's not really easy.
Okay, sounds good.
Yeah.
So it is kind of harder in the sense that non-degeneracy is something you would expect, or maybe that you would hope, but it's not immediately obvious.
Yeah, I mean, if you have, like, certain special cases, like a simplicial decomposition, then you can show it pretty explicitly by taking, like, a dual cell complex, but in general,
And is it also true for, like, with compact support? Like, when you take a, like, you do homology with compact support in a non-closed manifold?
There are more general statements that you can make than this. In this case, all we're doing is taking compact manifold.
I was asking if you know the dimensions of two vector spaces are equal. Do you already like know they're isomorphic through vector spaces?
This is
because they're
true.
free modules.
I guess the point here is, like,
You're trying to construct isomorphism.
yeah, so just like find explicit one coordinates.
I see.
Yeah, you want like an explanation as to why these two guys are
I see.
guess. Or another way to say it is that we'll like use this isomorphism in order to show that these numbers are equal.
Oh, okay, because we have it already proved.
Yeah.
Okay.
Yeah. So to prove this, we want to like construct some special representatives, and so the way that we do that is, if you remember, we had like these sort of like vector fields coming from electromagnetism, which were an example, etc. Whatever. And then on the sphere, for example, you have the volume form, or on a torus, you have this vector field that goes across uniformly. So these ones are like uniformly distributed across the entire manifold, and we want to sort of discuss how to construct these guys in general. And our hope is that these will give us the special representatives that we want and allow us to prove the things that we want to prove. Okay, so our idea was we wanted to sort of minimize variations. And so in order to do that, our goal ultimately was to minimize the integral of omega squared with respect to the volume of symmetric when A, d omega is equal to 0, and B, the homology class of omega is equal to some physical homology class. So within some physical homology class, you want to like minimize the norm squared. And to remind you what this is, at every point x, take an orthonormal basis d1 through dn of the tangent space x at m, and then dx1 through dxn is the rule. And so if you write omega as the sum of omega I dx I with respect to this basis, then norm of omega squared is equal to the sum of norm of omega I squared. So this is how we're defining the norm. Seems like a reasonable thing to do. And recall, in order to do this, need with a normal thing, which requires the use of the metric. Okay. So last time we discussed that if you have this sort of functional of omega, which is the integral of omega squared respect to volume, then what you want to do is to say that like a little variation in f of omega is equal to 0. And this is just analogous to the function in vector field case. You just want the little variation to be 0, and then this is a necessary condition to have a minimum.
Yeah.
Is your foot at the
Barely. I'll stop though.
So, yeah, so that is what we are aiming for. So we expect that this guy should be something like the integral of omega, like 2 times the integral of omega equal. This doesn't make sense. Right? Because this is like a K form now, and we can't like integrate K form over volume and get a number out. So what we really have to do, well, okay, actually maybe the notation is a bit wrong here. What I did last time was I subscripted with the point that we're looking at, which is omega, and I said we're going to take the variation with respect to some little variation here. So for motivation, if we look at our n, then if we take f of v equal to v squared, we know that the gradient of f is equal to 2v, but what does this mean? This means that if you take the gradient of f value at omega, then this is 2v dot omega, so v dot w. So what this means is that f of v plus w is approximately equal to f of v plus 2v dot w. So similarly, what we want to do is we want to perturb this guy a little bit by some variation theta, and then see how much he changes. So what we have is f of omega plus theta is equal to the integral of norm of omega plus theta squared. And I guess what you would want is that this is equal, or like I guess approximately equal to f of omega plus some sort of like 2 times the inner product of omega and k. So the point is that over here when we say norm squared, we define norm squared from an inner product. But over here we have this weird definition of the norm squared. So the question is, does this definition does this come from inner? So answer is yes, and we will construct this inner product, and then in fact show that the derivative of f is equal to this guy. Okay, so what is the idea? We construct something called a Hodge. Okay. Let me do this. Let me bar the x's to mean the ones which are orthonormal. And so I'll just define it like this. Star d omega I is equal, d xi is equal to dxj, where dxi wedge dxj is equal to dx1 to dxn. Okay, so what does this mean? You have a volume form which you have selected. And so I guess this is something to point out that you need in orientation. So we discussed this a little bit before that in orientation on a mathematical pen is a non-vanishing top form, and this tells you how to order basis functions. So it tells you whether a basis is positively oriented or negatively oriented at every point, and the fact that it's non-vanishing on the entire manifold tells you that this choice is consistent along the entire manifold. And so in this case, when we say dx1 to dxn, this is really saying that we're taking this with respect to the volume, to the orientation that we choose. So I guess here, E1 through En has to be an oriented orthonormal basis. Does that make sense? So question here is practice. Let's see. So let's say that we're working in R3. And so what is the star of dx1? Let's say that our orientation is dx1, dx2, dx3. So what is the star of dx1?
dx2, dx3.
dx2, dx3. What is the star of dx2, dx3?
Negative dx1.
Okay, so you say negative dx1.
Sorry,
We're
just
positive.
dx1.
Yeah, that should be positive because you put dx1 at the end, and then if you swap it over twice, you get two negative signs. Now let's say that instead of R3, we're working R4. So now you have a dx4. So what does this become in the first equation?
Add a dx4 at the end.
Yep.
And the same with the other one
Add
too.
a dx4. How about this guy?
Don't you add? You had the dx4 at the end. Oh, that.
Sorry.
Never mind. I thought you were gonna keep the same one.
No, it's negative dx.
Yeah.
Now it's negative dx1, right? Because if you added dx1 to the end, then you have to swap this across 3 times. And yeah. So in general, the formula is that if you take star of something, then if this is a k form, then this is going to be negative 1 power of k times n minus k omega. So why is this? Basically, it's because you have, so it's like dxi, then you go to dxj, such that dxj equals the volume. But then you go to dxi prime, such that dxj dxi prime is equal to the volume. And so these two guys are equal up to a plus or minus sign. what you have to do is you have to move each of these to the front. And so you have k guys over here, you have n minus k things over here. So if you move k things over n minus k things, then you can factor n minus k times n minus k negative things. Cool. So why is this useful? So extend to k forms by linear. So what does that mean? If okay, all of these should have this. So if omega is equal to the sum of omega I dxi r, then star omega is equal to the sum of omega I star dxi r. Okay? And so this is in n minus k. So you can sort of think about this as if omega is measuring, is you have some Rn, which you can think of as maybe tangent space to some point. Then if omega is measuring some projection onto a k-dimensional subspace, star omega is going to be measuring sort of a volume with respect to the orthogonal subspace in some sense. It's more complicated because you have k-forms which can't be written purely as the product of single one forms, but this is like sort of the idea that you're sort of measuring something orthogonal to it. So let me give you an example of where this comes up, or another way to think about this, I guess. So if omega is a k form, then star omega is an n minus k form. And so this is, so you have to integrate star omega over n, where this is an n minus k dimensional sub. So how do you interpret this? You should interpret this as quote unquote being the flux of omega through n. And so what do I mean by this? So dg, say you take some current j. So this is usually an electromagnetism vector, but instead what we're going to do is we're going to write this as j mu dx. Maybe get a little so if you have, I don't know if you have or have experienced Einstein's summation convention before, but what this means is you take the sum from I equals 1 to n of j I. So this is 1. And so usually you see something like Ampere's law or Coulomb's law, whatever. So you have to take the integral of j over some surface S, right, to see how much, like for example, the electric field passes through here, whatever. And this is equal to some charge q. Except this is a one form and this is a surface, so you can't do that. What you can do is you can take the Hodge star of this, and so what this does is it sort of measures the flux of your current going through this surface S. So that's one way that you can sort of geometrically interpret what this Hodge star is doing. Cool. So now let's define some sort of inner product. So this is what the Hodge star does, right? So if we want to write down norm of omega squared through the sum of omega I squared, right? And if we include the volume in front of this, then what we can do is we can rewrite this as sum of omega I dxi, omega I star dxj. Sorry, dxi. Great. And I claim that this is over all of these I, this is equal to the sum over I and j of omega I dxi, omega j star dxj. Where both of these have the length equal to. Can someone explain to me why this should be true? So I claim that like if you have some case where I is not equal to j, this doesn't come true.
They're like, I mean, they're complementary dimensions, so you'll have a repeated index. They're not-
Right. So what happens is like, if you have something here which looks like dx1, dx2, then over here, you only have n minus k things to choose from, and if you can't choose dx3, dx4, say you're in 4 dimensions, then you have to repeat dx1 or dx2. And because you repeat something, if you take the wedge part, it becomes 0, right? But this is just equal to omega wedge star omega. So what that suggests is we define inner product omega comma eta to be omega wedge star eta. And since we want a number, we should integrate this over manifold n. So this is, these are both A forms.
Just to be clear, we define the Hodge star in a base-dependent way, but it's like basis independent.
It's basis independent. You can show that under any coordinate change. Like, over time. There is like a sort of coordinate independent way to describe it, but honestly, I can never remember it, and I think.
Wait, I think some things like the exterior derivative are best in a basis.
Yeah. So these are k forms. So this one's also k. This one is n minus k. So their wedge is an n form, and so it makes sense to integrate this. Okay, nice. So what was our goal? Our goal was to analyze f of omega plus eta, which now we can see is the integral of omega plus eta wedge star eta. I should also mention that should be symmetric. But when I was trying it out, I got a negative sign, but I'm sure it is symmetric. You should Google it. I don't want to do it live. So this should be equal to eta comma. So it's sort of like a normal inner product. And since you have that omega comma omega is greater than or equal to 0 because it's equal to the integral of something squared, this implies that this is a positive definite on the space of k. Okay, so you have this guy. So now, I mean, you can just check the formula. It's bilinear, right? So this will be the integral of omega wedge star omega plus the integral of eta wedge star omega plus omega wedge star eta plus the integral of eta wedge star omega.
Wait,
And
can I
so
ask, sorry, what is the maximum generality in which this Hodge star exists, and why can't you get it in like higher? Like, what assumptions are we using here to define this Hodge star?
Basically that you have an orientation.
That's all.
Yeah. You can define a Hodge star with respect to any orientation. But it's convenient to do it when you have a metric. Right? You might need a metric. If you have a metric on a compact orientable manifold, that works.
But we didn't use a metric when we were defining it.
Yeah, we did. Because this, yeah, so this is a good point.
Oh, I see. Okay.
This has to be the orthonormal guys.
So it's only invariant under isometric base change.
Yeah. So the point is like,
Basis.
I was really confused about this because it's like, suppose I take like 2 dx1, right? And I try to say that the star of it is the thing where if you wedge it, you get the volume form. then this implies that the star should be 1/2 dx2 dx3. But because you want it to be linear, this implies that it should actually be 2 dx2 dx3.
And the latter is correct.
And this one's the right one to choose. So this is also something that confused me for a bit. But yeah, so this is why I can never remember like the coordinate-free description of it. It's something to do with the volume form. But the way I remember it is take the orthonormal base one forms and dualize it like this, and then extend by the negative. Does that make sense?
Yeah.
Okay, now we're done here. Okay, so this is indeed f of omega plus 2 theta, because he said this was symmetric secant, that's what it's around, plus theta. Okay, so I'm gonna ignore this because it's a order variation squared. So if your variation is really small, then this will be a really small number, so it doesn't really matter. So what we want to do is we want to set this equal to 0 for all a. Okay, so what does that mean? So this is to say that this guy is the derivative of f at omega with the variation eta, which is similar to the gradient of f point x out of the vector. Okay, so what does this mean? This means that the integral of omega wedge star eta should be equal to 0 for all eta. Okay, so what does this tell us about omega? So suppose omega is non-zero at some, right? Let's say some point x. Okay, so can choose eta with support in some epsilon ball of x, such that omega wedge star eta integral this is greater than 0. So basically what we do is like we can essentially take eta is equal to omega times some phi, which is some cutoff function. And so what this does is like if omega looks like this, and this is your point x, then eta is going to look like that. And so if you take omega wedge eta, then you're going to get something non-zero near x, and because it doesn't really care away from x, that's fine. And if you choose a small enough ball, then if omega is non-zero, then it'll quote-unquote have the same sign everywhere nearby, and so you can prescribe this to happen. So you can choose eta in such a way that this is true. So what this means is that omega is equal to 0. Does that make sense?
Why do you need the support of eta to be like localized around?
You can choose it. So if you have something like this, then what can happen is like if you have that this is what omega looks like, then if you have eta looks like that, then omega wedge star eta, you get a positive contribution here and negative contribution over here. So it can still be 0.
But we chose eta to be omega times the cutoff. Like, why didn't you just choose it to be equal to omega and then remove the cutoff function? Like, why can't you?
Oh, I mean, yeah, I guess that's true. Yeah, honestly, okay. I was thinking of it like this, but also just like choose eta equals omega, and then I guess omega wedge star omega.
Yeah.
So what this implies is like, if you want this to work for all possible variations, then you need to have that omega is identically 0. Which is not what we want, because we want differential forms, not something that's just 0. So let's look at the analogous case in Rn. what we're saying is that if we have like this is basically like a parabola, right? Because we're just essentially trying to minimize norm squared, and this says that the minimal value is at 0, which makes sense. That's what we expect. But here what we fail to take into account is that we want the conditions that d omega is equal to 0 and that omega is equal to some fixed co-multiples, right? So if we take these into account, what happens? So let's say we set omega prime to be omega plus eta. So eta can't be arbitrary because we need that d omega is equal to 0. Or I guess in this case, d omega prime is equal to 0. So since d omega is already equal to 0, what this implies is that if we take d of both sides, that d eta is equal to 0. Because we want this to be 0, d of this to be 0, and d of this is already 0. So this implies that d is equal to 0. So already this means that we can't choose an arbitrary variation, right? But moreover, we want this to be a fixed co-multiples. So what that means is that this variation, omega prime, should be equal to the co-multiples of omega. What that means is that the co-multiples of omega prime minus omega is going to be the 0 co-multiples. What is so that means that this is the co-multiples of eta. What does it mean for eta to be in the 0 co-multiples?
That means it's the kernel from the maps.
Well,
It's an image.
From the map.
right. And what's the map?
Boundary operator.
Right, the cobanding operator. So this means that eta is equal to d eta prime. So what that means is that the only variations that you can choose in order to guarantee that both these conditions are still true are exact variations. So what we should do is we should not vary with respect to arbitrary variations, but we should only vary with respect to exact variations. So I guess I'm going to be using eta to be the guy that you're taking the exterior derivative of here, but it's the same idea. And this is equal to omega comma omega plus 2 omega comma d eta. I guess I'll just say approximately. Right? And so we want this to be equal to 0 for all eta. So what does this mean for our omega now? So we have this guy, right? By symmetry of the inner product, this should be equal to the integral of d eta wedge star omega. And now what you're going to do is you're going to say integration by parts. It's going to be equal to plus or minus integral of eta wedge d star omega. Right? So why, I mean, integration by parts, it's like, this is a derivative, so we expect integration by parts to hold, but formally, why is this true? This is true because if we take the integral of d of eta wedge star omega for our manifold M, we know that this is equal to 0 because of Stokes plus M is closed. And this is equal to the integral of d eta wedge star omega plus the integral of, or plus or minus the integral of eta wedge d star omega. So what that means is that because this sum is equal to 0, d eta wedge star omega is equal to plus or minus eta wedge d star omega. And so for convenience, we can throw in another star here. So we can say star star. This offsets us by another plus or minus sign, but it doesn't really matter. And this is equal to the inner product of eta and star d star omega. So now we have that this 1 is equal to 0 for all eta. And what this means is that star d star omega is equal to 0 for all, actually not even for, this is like the same argument as before, right? If this guy is non-zero, then we can choose eta to pair with this guy, non-trivial. Okay, so let's look at what this sort of object is. So star omega is in n minus k form. Take d of that, and that becomes n minus k plus 1. And if we take star of that, then that actually becomes a k minus 1. So I'm going to define this to be this operator, the superscript star omega. And I think this is sometimes called the codifferential or whatever, and sometimes people say that d star omega equals 0 means that it's co-closed or something. But this is interesting because if you look at your sequence, which goes like omega 0, omega 1, omega 2, then we have these operators d which go to the right, but now we have these operators d star which go to the left. And we're saying that our hopefully norm minimizing forms, we already know that d omega is equal to 0. So we should satisfy the two conditions, d omega equals 0 and d star omega equals 0. Any questions on this?
Could you go up for a second?
Yeah.
Just to your derivation of eta with star d star omega should be 0.
Yeah, I guess I went through this kind of fast. The idea is you want this to be 0 for all n. But then here you're taking the derivative of the variation, so you want to move this derivative over to the other side, omega. And so the idea from calculus, if you've ever done calculus of variations before, is to do integration by parts here. And so the first thing you do is first you flip this around and have the star on omega so that you can get rid of the star. And then you do integration by parts to move the d to the other guy. And then because we want to, because it would be nice to write this as like the inner product of eta with something still, just throw in 2 stars there. I guess this should still be a plus or minus. Yeah.
Oh, okay. Because you don't want there to be any variation in your inner product of eta with star omega, and then you expand by integration by parts, cancel out the term that vanishes, because we know that d eta is 0. This is for all closed eta, right?
No. No, this is for any eta, because the argument is that, sorry, I kind of changed out around.
Oh, eta is eta
calling
prime?
Eta. Yeah, so here I'm calling eta prime as eta.
I see. Oh, right, okay.
Yeah, I kind of changed notations a little bit there because I didn't want to keep breaking it.
Okay, that makes sense.
So, sort of an analogy here is if we look at Rn again, what we can do is we can say, okay, so you have some sort of paraboloid which you want to minimize, and let's say that you start off at this point. But you can't move in arbitrary directions. You have to move restricted yourself to this point. So if you do that, what happens is you get this one-dimensional parabola, right? And now, if you move down along here, you have a minimum which is non-zero. So that's essentially what we're doing. We're restricting the directions in which we can move in, and what that does is we find a minimum which is non-zero norm. And this is essentially taking just like a square norm in infinite dimensions. So everything that we can do in infinite dimensions, we should be able to find something in lower dimensions, which is like the same idea. And yeah, I guess this condition that star d star omega is equal to 0. This is equivalent to sort of saying that the gradient at this point is not 0, but it is perpendicular to the plane of the directions that you're allowed to move. So that's essentially what this condition is saying. And you can sort of see that because this d star, the reason I call it d star is because it is the adjoint of the differential operator with respect to the center product of theta. So all we're doing here is infinite dimensional linear algebra. So one thing I should note is that in general, del f omega equals 0 does not mean omega is minimizing, right? So you can have maxima, you can have saddle points and whatnot, you can have that sort of behavior, but in this case, and this is really easy to show because we take f of omega plus d eta, then what is this? This is equal to omega comma omega plus 2 omega comma d eta plus d eta comma d eta, using the same expansion that we had earlier. This is equal to 2 d star omega comma eta. So once you know this is the formal adjoint, it's pretty easy to manipulate. You just move it across the other side of the inner product and throw in a star there. And we know that this is equal to 0 because this is equal to 0. So get rid of this term, and then this is greater than or equal to 0, this is greater than or equal to 0, and sorry, we would actually need the first place. The second part is greater than or equal to 0. So what that means is that if you take omega prime is equal to omega plus d eta, then f of omega prime is greater than or equal to f of omega, which equality if and only if d eta is equal to 0, which then implies that omega prime is just equal to omega. Any questions? So this, so what this implies that omega is actually minimizing. And this is nice because there is a unique minimal representative. So what this means is that to any homology class omega, we can associate to it this omega bar such that omega bar is inside this homology class, and omega bar is norm. So we found like a special representative for, and I guess just say there exists a unique omega bar such that these are true. So there exists a unique norm minimizing thing, and this allows us to find special representatives for each homology class. And the conditions that this omega bar has to satisfy is that d omega bar is equal to 0, and this is just so that it is a homology class, and then d star 0, and this is so that it is and to bring it back up to this picture, this depends only topologically, right? The exterior derivative is something that we defined, it only depends on the topology. This depends on the metric. So that is to say that the second equation that we have is depends on what metric we have, and so if we choose a different metric, then we're going to get different representatives for this sort of special class. So yeah, this makes sense because, for example, if we were to take the sphere, then sort of the volume, or let's say torus. This thing almost dead.
Do you have a charger?
A USB-C.
Let's hope I can still write this. Okay. So let's say that instead you have a torus, and you have this sort of one form which is uniformly going around. Well, if you sort of like compress part of the torus, right? Or you stretch the torus out to make it sort of like this, and then but you have some sort of like a stretched out torus, right? Then you might see that like maybe if you just go around the same amount, initiation won't be good. You should maybe like compress or like stretch out the forms in some directions. So it makes sense that the sort of uniform shape should depend on the uniform forms should depend on the shape of our manifold. So yeah. Let's look at some examples. So, example number 1. Can someone give me an example of a form that they think could be a Hodge form
On any space.
on any space? Very simple form. Very simple zero form.
It's a zero.
Like constant?
Yeah, so constant functions, right? So constant functions. So if you have f is equal to c, then we already know that df is equal to 0. But what is d star f? So d star f is equal to star d star f, right? And this guy is some n form. So that means is that this guy is automatically equal to 0, right? Because there's no n plus 1 forms. So indeed this is equal to 0, and so these are Hodge forms. Nice. Secondly, dual to that,
Wait, why doesn't that work for every zero form?
because of this condition.
Oh, I see.
Yeah. So it's interesting. Second one, can someone give me an n form, which they expect to be which they expect to be sort of, I'll say norm minimizing, but in this case, which is uniform.
Like the volume form?
Yeah,
Like
right?
dx, or like all of them.
Right. So I think we'll answer the same thing. So you take the volume form, and then let's call this omega. So d omega is not meant to be equal to 0 because it's an m form. D star omega is equal to star d star omega. And what do you think star omega should be?
1.
Yeah, so it's essentially 1. It might be -1, I'm not sure, but based on the definition, it's something that you need, or no, it should be 1. It's something you need to put together the volume form, right? So, well, the volume form times 1 is the volume form. And so that means that this is equal to 0, and so the star omega is equal to 0, and again, we have another Hodge class. Third example. Let's look at Tn as being Rn modulo Zn. Okay? And let's say that we look at omega k. What do you expect to be Hodge forms here? So this is the torus is Rn modulo lattice.
Like what degree?
Any degree. What if we start with one forms?
Like things that are like around the torus.
Sure. So that would be something like dx1, right?
Mm-hmm.
Or something like dx2. So the point is, or you can even have like in higher degree something like dx1, dx2. The point is that the coefficient is constant. And we can do this because Tn is Rn modulo something. So it makes sense to identify these vector spaces at different points. And so if you have a sort of constant form, then it turns out that you have a Hodge class. Cool. A word of warning. Let me see if I can. So, warning, these equations are not real to solve one day. So if you do physics, then you just say, I'm happy with writing the equations down and I'm going to assume that they have solutions because if they didn't, then the world wouldn't be the place. If you're a mathematician, then you have to check some things. And so, for example, the reason is because we're working over compact randomly. So I think our experience with ordinary differential equations sort of leads us astray because ordinary differential equations always have a solution. But these are partial differential equations because there's multiple independent variables which are the different directions. And what happens here is you get something a bit more difficult because, for example, if you had something like solving the Laplacian equals 0 on some disk with some specified boundary condition, then you can uniquely find a solution. The thing is, the solution depends on the boundary condition. Now imagine they take two disks and glue them together to become a sphere. Now you no longer have the boundary condition. So how do you make sure that like these two solutions can like glue together in a satisfactory way of things to work? So that's one example of an equation. But I mean, in general, it's like it's just not as obvious as you may expect that these solutions exist. So if you, I won't go over this because it's some technical analysis, which I'm also not great at. But if you want to search it up, look up harmonic theory. Sorry, not sorry. Elliptic PDE theory. Okay. The last thing that I want to do is, before we prove the two theorems, is to talk about the Laplacian. Okay, so what is the Laplacian? So as I said, you have to satisfy these two equations, d omega equals 0 and d star omega equals 0. These are a bit annoying because this guy goes from omega k to omega k plus 1, whereas this guy goes from omega k to omega k minus 1. So it'd be nice if you had some differential operator that took some space and ended up back in the same space. So what you can do is you can note that these two equations are true if and only if d omega comma d omega, so the norm of this guy squared plus d star omega comma d star omega is equal to 0. So why is this true? Because both of these are greater than or equal to 0. So if their sum is equal to 0, then that each one of them is individually 0. And because if you have something which norm squared is equal to 0, then it itself must be 0. Okay, so we can rewrite this. This guy, because of the adjoint of D, is D star D omega comma omega, right? We just move this over to the other side and pick up a star. And then this guy, again, we can move it to the other side and pick up a star, and then you get D star omega comma omega. Together this equals 0. So now we can combine these two and say that D star D omega, so D star D plus D star omega comma omega equals 0. And this would easily be satisfied if this guy was true, then this would easily imply this, right? So this operator, D star D plus D star, is called the Laplacian for one of them. There are many ways to get a Laplacian, but this is one way to get a Laplacian. Maybe it would be more accurate to call it a Hodge Laplacian. And so if this equation is true, then this is going to be satisfied, which would imply that these two are true. But if this is true, then D omega and D star omega are both 0. So automatically you have that D omega and D star omega are both 0. So these two conditions are equivalent to each other. So that means is that this set of equations, D omega equals 0 and D star omega equals 0, is equivalent to just this one differential equation of the Laplacian omega. And so here's the thing. D star goes from k to k plus 1 back to k. And this one goes from k to k minus 1 back to k. And so you have that this Laplacian goes from omega k to omega k. And so why is it called the Laplacian? Well, if you look at Laplacian on omega 0, then what you end up finding is that it's essentially the divergence of the gradient, which is the usual Laplacian that you have. And on omega k, it'll be something similar to like take the derivative squared. I'm not sure exactly what the computation is, but there will be some plus metric. There will be some metric terms, and there will be like two derivatives, but it'll roughly look like to highest order take the derivative squared in terms of each of your coordinates and add them all up together. So it does look like some sort of Laplacian.
Is this like, it looks kind of like a chain homotopy related, is it?
No. But this is also nice because it's one differential equation set. Okay, so in the last 15-ish minutes, let's prove our two theorems. One very So as was stated, we have this wedge product from hk to hn minus k. So that's from hk cross hn minus k for r, which sends omega comma eta to the integral of omega wedge eta. And we saw that for Tom classes, this is the intersection. Cool. So what we want to show is this intersection pairing satisfies the following condition, that if omega is not equal to 0, there exists an eta such that integral of omega wedge eta is not equal to 0. Someone give me and if this is true, if this is true, then the intersection pairing gives isomorphism of hk is isomorphic to hn minus k. So yeah, I guess what I wrote above was not quite true, where you want an isomorphism between the vector spaces. Instead you get an isomorphism of one vector space with the dual of the other vector space. So hope this answers your question as to why I want this isomorphism. Yeah. So can someone give me such a candidate eta? Something so that if I integrate omega wedge this guy, it will be non-zero. I'll give you a hint. If you take a vector and you want to take the dot product with something and get a non-zero number with you want it, then that's second input.
Is it like the Hodge star?
Exactly. So if you take eta is equal to star omega, then that implies that rho of omega wedge star omega is equal to the norm of omega squared, is equal to 0, and is equal to 0 if no omega. So you may say that this proves Poincare duality already, but there's something to check. You may check that this is cohomology class. So it's not so obvious that if the omega is equal to 0, then that implies that the star omega is equal to 0. But we know that the star omega is equal to 0 if omega is harmonic form, which I guess we could say these two conditions are called being harmonic. So harmonic form means the Laplacian vanishes are equivalently these two conditions. And if this is true, then this implies that E star omega is equal to 0, which implies that E star omega is equal to 0. So we can't take such an omega, we can't take such an eta for any omega, but given a metric, we can choose some omega prime such that homology classes are the same and omega prime is harmonic. And then we know that the integral of omega wedge star omega prime is equal to the integral of omega prime wedge star omega prime. And that's because these two are part of the same cohomology class and the severe frequency.
But why does being part of the same class mean?
It's because omega prime is equal to omega plus beta.
Oh, yeah.
And so yeah, it's like an integration vector. So that means like Stokes theorem, essentially, right? And maybe there's some steps I'm leaving out, but on board steps.
Yeah.
Any questions? So it's like a pretty easy construction, right? Like once you have the machinery of like these special representatives, somehow the condition for being harmonic like guarantees that Poincare duality is true. I'll start with the Kunneth formula. And so again, the idea is like you have this m across m, and you have two projections come up to m and down up to n. So if you have an omega over here and beta over here, we call pi 1 and pi 2. What you consider over here is pi 1 star omega wedge pi 1 star beta. So in sort of the vertical directions, it's in fact of this guy. In sort of the horizontal directions, it's measuring this guy. So our hope is that I'll call this omega wedge beta just because I don't want to keep writing pi's. our hope is that omega wedge eta is a homology class, and this is the hard part. So this isn't too bad. The hard part is that we get everything. Okay, so and omega wedge eta in cohomology. So these are the hard parts. Let's discuss this one first. So we have E pi 1 star omega wedge pi 2 star eta. This is equal to D of pi 1 star omega wedge eta plus a similar thing. And then we can swap these two around to get pi 1 star d omega is equal to 0, wedge eta. So in effect we get 0 to 0, so we know that that basis is a cohomology. Is that fine, or was that a bit too fast? Now we have to show that two things. First, that we get every cohomology class, and second, that this is not true. So this one is or yeah, this one is a bit easier to show. Essentially, what you do is so what happens is you have a metric on n, you have a metric on m, and these two induce a metric on g m plus. So what happens here is if you have some point x and some point y over here, then some point in gm plus n would look like the pair x comma y. And the metric in this space is as follows. You can decompose t x comma y of m plus n into two parts, which look like ty of n and tx of m. And so you declare that on this guy you use the metric on m at the point x, and on this guy you use the metric on n at the point y, and that these two subspaces sort of follow each other. So this defines a metric on the product. And with respect to this metric, the claim is that the Laplacian on n cross n of omega wedge eta, where again by this I mean take fullbacks and whatnot, is equal to the Laplacian on m of omega wedge eta plus omega wedge Laplacian on m. So this is an exercise. I'm 70% sure that this is true. I may have written it down incorrectly. But or you can check out this paper. It discusses complex geometry, but it has quite a nice discussion of Hodge theory, which I can see. So if omega and eta harmonic, then this implies that omega wedge eta is also harmonic. And in particular, if omega and eta are non-zero and harmonic, then this implies that omega wedge eta is non-zero, right? Because if it evaluates something non-zero on the vertical part, like omega evaluates something non-zero on the vertical part, and eta evaluates something non-zero on the horizontal part, at x and y, then at the product point x comma y, you have something which is non-zero. And because it's harmonic, this means that it is the special representative in its cohomology class. So that means that the special representative is non-zero, and if the special representative is non-zero, that means that the cohomology class itself is non-zero. So this means that omega wedge eta is not equal to 0 in cohomology. Does that make sense, or do you want me to write something this way? If that is okay, then the last thing is I'm gonna go a few minutes over just because I want to finish up the story. If you look at so how do we know? Do we get? So we're gonna need something a bit stronger than just Hodge classes in general. What we're gonna need is tool, which is the spectral theorem over function. And what this says is that there exists an orthonormal basis for omega k of m with respect to this omega wedge star eta inner product, such that I guess I should call these omega I, such that the Laplacian of omega I is equal to omega I of omega I. So there exists like an orthonormal basis, which form like eigen k forms of the Laplacian. And so in simple terms, if you look at Qn, then what these are is it's basically cosines and sines. And I should say complete. And so what I mean by complete is that for all omega inside omega kn, there exists Ci such that omega is equal to the sum of Ci. And so on Tn, this will be something involving cosines and sines, or even simpler, I can be more explicit and say on S1, this will actually be cosines and sines. And this condition is essentially saying that f of x is equal to the sum of Ci e to the I in x, or the real and imaginary parts here. And so this is a generalization of frequencies. Okay, so how does this tool help us? Well, this says now that so if omega I is a basis for the Laplacian on M, and eta j is a basis for the Laplacian on N, then this implies that omega I, which eta j is a basis for Laplacian of M times M. So what that means is that any psi inside omega k, or I guess I could say this can be in I form. This can be in M form, and this can be in N form. Such that M plus N equals K, and so this is the Laplacian on K. so this is basically linear. So what that means is that for any psi m cross n, we have that psi is equal to some sum of Cij omega I beta j. And if you look at the Laplacian of psi, then you can check that this is just equal to the sum of Cij Laplacian on the m part of omega I beta j plus omega I times the Laplacian on the n part of beta j. And because these form the orthonormal basis as above, then this is equal to sum of Cij lambda I, like the ith eigenvalue on m omega I beta j plus lambda jn omega I beta j. So this is equal to the sum of Cij of lambda I j on m and n of omega I beta j.
Plus?
Hmm?
Plus?
Yes. Okay, so another key point here is that each lambda is greater than equal to 0. And the reason for this is that if you look at the inner product of the Laplacian of eta comma eta, and let's say that this is an eigenvalue, so then this will be just lambda eta comma eta, which will just be lambda times no eta squared. But this is equal to, as we saw above, the eta plus the star eta. This is also greater than or equal to 0. So this guy divided by this is equal to lambda, so that means that lambda is greater than or equal to 0. So in effect, if we say that the Laplacian of psi is equal to 0, which means that it's a Hodge class, and we know that every cohomology class has a Hodge class, then this implies that on this guy, whenever Cij is not equal to 0, we must have that lambda im and lambda jn are both equal to 0, which then implies that omega I and beta j are harmonic. Which then implies that if you take the sum of products of harmonic classes, that's the only way that you can get harmonic class. So what this means is that we do in fact get everything, because every cohomology class is a harmonic class, and the only way to get harmonic classes is by sums of products of harmonic classes. And that proves Kunneth formula modulo this spectral decomposition theorem and other analytical technicalities. Any questions? Overall? Next week, I think I'll start with some nice comments on Hodge theory, and then we'll start talking about a little bit about vector bundles, connections and curvature, and probably I think we have 2 weeks left, so we're probably going to talk about connections, curvature, and then maybe a little bit about these ideas applied to Riemannian geometry. That's the goal for this class. Cool. So that's all for today.
Wait, Harish.